Hello everyone, welcome back to MP Coding. This is the Linux device driver development with Raspberry Pi video series. Today, we are going to talk about kernel linked lists. First, let's understand what a linked list is. A linked list is a data structure that stores a sequence of elements, called nodes. Each node contains some data and a pointer to the next node. In a singly linked list, traversal is possible only in one direction, from the first node to the last node. In a doubly linked list, each node contains two pointers, one pointing to the next node and another pointing to the previous node. There is also a cyclic linked list, where the last node points back to the first node and first node points to the last node, forming a loop. Linked lists are widely used in the Linux kernel to manage dynamic data efficiently. They are used for task management, device lists, memory management, and many other internal kernel structures. If we compare a normal array and a linked list, a normal array stores its elements in contiguous memory locations. That means each element is placed one after another in memory. On the other hand, a linked list does not require contiguous memory. Its nodes can be stored anywhere in memory. Each node stores its own data, along with metadata in the form of a pointer to the next node or the previous node. Because of this, linked lists do not require continuous memory like arrays. Okay, let's move on to the code. Here, I have copied the Hello World example code into a new folder called linked_list. Then, I renamed the source file to my_linked_list.c, and I also updated the make file. In the module description, I changed the description to kernel linked list example. At the moment, the init and exit functions are empty. Now, at the top of the file, I will define a data structure that we will use as a linked list node. First, we need to include the Linux list.h header. Struct my_data. Here I will add uint32id and the char array to store the name, just for data. Struct list_head list. This list_head member stores the metadata for the next and previous nodes. If we open the types header file, we can see that list_head is simply a structure containing two list_head pointers. This implementation is used for a doubly linked list. We can also see two other related structures. The first one is h_list_head, which is used for a singly linked list. The h_list_node structure is used to represent a node in a singly linked list in the Linux kernel. It contains a pointer to the next node and a pointer to the previous node's next pointer. This design allows efficient insertion and deletion without needing a full doubly linked list. The h_list_node structure is mainly used in hash tables, where memory efficiency is important. Compared to list_head, h_list_node uses less memory because it stores fewer pointers. Next, we need to create and initialize an empty list. For that, we use the list_head macro. We need to pass a name, and here I will use the name my_list. This macro creates and initializes the list at compile time. If we open the linux/list.h file, we can see that the list_head macro initializes the list_head so that both pointers point to itself. When a list head points to itself, it represents an empty list. Now, inside the init function, I will declare two pointers of type struct my_data, named tmp and next. These pointers will be used to access the linked list elements. Next, I will declare a pointer to struct list_head. This pointer will be used to iterate through the list later. I will explain this in detail when we traverse the list. Now, I will allocate memory for the tmp node using kmalloc. tmp = kmalloc. Pass the size of struct my_data and the GFP kernel flag. I have already explained kernel memory allocation in the previous video. If you are not familiar with kmalloc and GFP flags, please watch the last video in this series. If tmp is null, it means the memory allocation has failed. In that case, we print an error message and abort the initialization. Here return error, no memory. If the allocation is successful, we can now initialize the data. I will set the ID field to 0 and copy the string MP coding into the name field using string copy. Now that the data is ready, we can add this node to the linked list. For this, we use the list_add_tail function. Here, we need to pass the address of the list_head member inside our my_data structure, which is list, and the address of the list head that we need to add this new node, which is my_list. This function adds the new node to the end of the linked list. If we open the Linux list.h header file, we can find many helper functions related to linked lists. For example, list delete, list replace, list swap, and list move. You can explore these functions to get an idea of what they are used for. Now, let's get back to our code. Next, I will copy and paste the same code once more to add another node to the linked list. In this new node, I only change the data fields. I set the ID to 1 and the name to Hello World. Now, there is a problem here. If this memory allocation fails, and we return immediately like before, we do not free the memory that was already allocated earlier. This will cause a memory leak. So, we need to free all previously allocated nodes before returning an error. To do that, at the bottom of the init function, I will add a label called mem_free. If any memory allocation fails, we will jump to this label. Since we are using a linked list, we need to iterate through the list and free each allocated node. For list traversal, the kernel provides several iteration macros. Each one is useful for different situations. When we want to delete list entries while iterating, we should use the safe version. In this case, we use list for each entry safe. Now, let's look at the parameters. The first parameter is a pointer to the current node, which I will give TMP pointer. The second parameter is a temporary pointer used internally during iteration, which I will give next pointer. The third parameter is the list head, which is my_list. The last parameter is the name of the list_head member inside our structure, which is list. Inside the loop, we first remove the node from the linked list using list_del. Pass the current node list head, which is TMP list. Then, we free the memory using kfree, because the memory was allocated using kmalloc. Pass TMP, current node. After freeing all allocated nodes, we print the error message and return the error code. Copy these lines and paste it here. Now, whenever a memory allocation fails, we simply jump to the mem_free label using go to mem_free. Set this first one also, since this first one still no list members, so it will just skip the list iteration and just print the error message and return the error code. This ensures that all previously allocated memory is properly released. Now, I will add one more node to the linked list. I simply copy the same code once again and change the ID and name fields. At this point, we have added 3 nodes to the linked list. Now, let's iterate over the list. As before, the kernel provides multiple iteration macros. For this example, I will use a simple one called list_for_each. The first parameter is a pointer to struct list_head that will be used as the loop cursor. The second parameter is a pointer to the head of our list, which is my_list. Inside the loop, we need to get the parent structure that contains this list_head. For that, we use the list_entry method. We pass the current list_head pointer, which is ptr. Next, the type of the structure, which is my_data. And the name of the list_head member inside the structure, which is list. Now, we can access the data fields and print them. Here I will print the element ID and the name. Now finally, before exiting the init function, I will add a print messages. In the exit function, we need to free all allocated memory. For this, We can simply reuse the same cleanup code that we wrote under the mem_free label. So, I copy that code and paste it into the exit function. We also need to declare the same pointers used for list traversal. So copy that line and paste it here in the exit function. This ensures that all nodes are removed from the list and their memory is released. Finally, add the print message like "Goodbye kernel" to indicate that the module is unloaded. Now that everything is ready, let's build the kernel module. Navigate to the source directory, type make, and press enter. You can see that the module is built successfully. Before loading the module, open the D-message buffer in a separate terminal. Now, load the module. You can see that the list iteration works correctly and all element data is printed as expected. Next, let's unload the module. You can see that all allocated memory is freed correctly. This is how we can create, add, iterate, and delete elements using kernel-linked lists. Now, you can experiment on your own and try some common linked list operations, such as reversing the list order. That's it for today's video. Today, we discussed kernel-linked lists, how to initialize a list, add elements, iterate through the list, and delete elements safely. In the next video, we will move into the real hardware section, starting with GPIO, interrupts, and timers. So stay tuned, like and subscribe, and see you in the next video.